Hello, this is Dan Allford with ARC Specialties. I'm in Chicago at McCormick Center at 2025 Fabtech. I'm here with Dr. Adam Stevens. We're working on a couple of projects together, and I'll let the doctor tell us what we've got here in front of us.
Thanks, Dan. This is ESAM. It's Electro Slag Additive Manufacturing. And we're looking at this for producing very large components that are conventionally cast and forged. So think of a hydropower turbine, for example, or a component of a nuclear reactor. These are parts that are tens of tons, tens of thousands of pounds, and they're difficult to produce through conventional means because of very long lead times. So what we're looking at is using a process that was evolved for cladding and adapting it to building up thick layers at high deposition rates.
So this is actually a 100-year-old welding process, isn't it?
Yeah, it is. The electro slag process, depending on who you ask, was either invented in the United States in the 1930s or 1940s, or behind the Iron Curtain in Ukraine around the same time period.
And the big advantage of this process is deposition rate, right?
Yes, that's right. And it was originally invented for joining large plates in the vertical up condition, and then it evolved into high deposition rate cladding applications in the horizontal position. And now we're pairing that with modern robotics and toolpath planning in order to produce arbitrary shapes and build those up. And we're no longer constrained to simple bodies of revolution or just vertical up joints.
I think most people that are watching us today are probably familiar with wire arc additive, where you use a 1 millimeter wire and you get a 2 millimeter bead, but this is a little bit different, isn't it?
Yes, yeah, here we're using a 30 millimeter strip in this case, but there's a lot of different ways we can
We're going to
use
go to 60, right?
We do want to go to 60, yes. 60 millimeters or more. This is a 30 millimeter strip. It uses approximately 500 amps to melt that strip. And we have a granulated flux that visually looks very similar to submerged arc welding. So you have a granulated flux. At the very beginning of the process, there is an arc, and you can see that, a little bit of flash. Then that arc melts some of that flux and it forms a molten slag. And from that point onward, all your process heat evolves in that molten slag. And it's all the I squared R heating in that slag layer, just like the I squared R heating in your toaster. So you have that glow.
And so in a single pass, we're getting a deposit that's 30 millimeters wide.
Yeah, just very proportional to the width of your strip, maybe a little bit wider. And the name of the game is to control the trajectory of that path and use modern tool pathing to locally keep your deposit level in order to contain that flux and slag layer and allow it to solidify. And then the neat thing about this process is it's similar to submerged arc welding, and a difference from some of your gas-based welding processes. This slag layer is either liquid or solid after it solidifies, and it stays on top of that weld bead until the bead cools to a certain critical temperature, after which the slag cracks off naturally and it leaves a beautiful unoxidized surface. So it's very high quality.
And I think that's key to it. I see a whole lot of oxides on all the additive manufacturing stuff, and I can't believe that that's not detrimental.
Yes, that's something that we've seen as well in the laboratory. And that's one of the reasons that we moved over to this when I was doing some background research, is we need something to keep that oxide from forming.
So we'll be up at 50 pounds an hour deposition rate before we're over.
At 60 millimeters, more if we're using wider strip, or if we're even using multiple robots, because there's a lot of work that we've done at Oak Ridge National Lab using multiple robots to coordinate motion. There's no reason you can't extend that to strip-based processes. So 50, 100 pounds an hour, and then it's all a question of how do you balance your heat input. The nice thing about this process, the electro slag process, is that it's pretty low dilution, so your heat affected zone into the previous layer is low.
Small.
Yes, now it's a huge bead and it cools slowly, but if you look at the heat per unit mass deposited, it's actually quite low, and that's great for additive. And it scales particularly well to really big parts, and that's what we're looking at here. That's why we're looking at these big parts that are conventionally cast and forged.
Well, in welding, the definition of productivity is deposition rate, and so at 50 pounds an hour, that looks pretty good when you compare it to 2 or 3 pounds an hour of wire.
Oh yeah, absolutely. And when you're looking at a 70,000 pound part, that adds up.
So this is the first time ARC Specialties has ever collaborated with a national lab. and it's working out pretty well for us, but other people might not be familiar with what is your mission statement? What do you do?
With Oak Ridge National Laboratory, we are a Department of Energy laboratory. There are many laboratories across the country, well over 10, and our goal is to support energy production in the United States in many different forms. And that involves fundamental science and more applied science and engineering. Within Oak Ridge National Laboratory, I work at the Manufacturing Demonstration Facility. That is a facility that specializes in partnering with private industry, companies like yourself. Exactly. And we are funded by the Department of Energy Advanced Materials and Manufacturing Technology Office, AMMTO. And the ways we're working together include what are called collaborative research and development agreements. And that provides us a vehicle, a contractual vehicle, for working together to develop technology and leverage the expertise of private industry. And then you get to work with us, we get to study the process, we get to look at the science, and we get to work with you because you can build and you can do engineering and you have the expertise of building systems that have to live in the field, and together we can do things that we just can't do on our own.
So right now it's depositing over 20 pounds an hour.
Yes.
So we're building a part.
Yes.
Right now.
Yep. Right now.
So what's the ultimate goal here? You're trying to create a whole new technology. It sounds like.
Yes. A whole new manufacturing workflow, manufacturing pipeline for very large parts that are conventionally cast and forged. And it's not going to replace casting and forging. It's going to complement casting and forging. Things where maybe you need something quickly. You need something that can't be produced any other way, because the nice thing about additive is you can mix materials. Obviously there's engineering that needs to be done to do that. You can't just throw it together and mix materials and it works instantly out of the box. There's R&D that goes into that. But that's why it's a research program, and that's why additive is so exciting. So it's not enough just to, and we don't want to replace casting and forging, we want to make the next generation of things that are conventionally cast and forged, really big parts, mass at scale.
So this is actually stainless at this point. So it's not inconceivable we could make the inside of a vessel with stainless and then the outside with some kind of high-strength steel.
Absolutely, absolutely.
Pretty exciting times.
Yes.
That's why I'm enjoying working in additive manufacturing right now, because at this point, nobody knows which way the field's going to go.
Right.
And I really hope that this ESAM system is part of the future of additive manufacturing.
So do we. And if there is any role to play for something like ESAM and way for the Department of Energy and the lab ecosystem to help, and we're here for it.
We appreciate all the work.
We appreciate working with you. It's been great. Thank you.